Okay, so shall we start the next talk? Yeah, the next speaker is Norihiro Iizuka from Osaka University, who is going to tell us about defining entanglement without tensor factoring, a Euclidean hourglass prescription. Please start.
Okay, good morning, everybody, and thank you very much for the invitation. And okay, so let me start. So the title of my talk is about the hourglass prescription. So before I go into the detail, let me introduce my collaborator, wonderful collaborator, Dan Kapat. You probably know it. Then Takanori Anegawa is my student, who is very, very good. So my talk is about the hourglass, so sunadoke in Japanese. So what I want to emphasize is that this neck or waist, you call, is so thin, but it's non-zero. That's an important point. Okay. So let me start with a brief overview of my talk. So I first explain, this is total review about the entanglement for the gauge theory, what kind of approach we have so far, and what is I would say the issue we face, and then how can we propose by this new proposal. Okay, so our new proposal is this hourglass prescription. Okay, and then we show several examples how this example works for simple case in the beginning, and then go to the more complicated case, and then left some open question as a future problem. Okay, so that's a plan. So let me start with a very, very basic of the entanglement. Okay. So let's consider the field theory in d plus 1 dimension. Whenever I say d plus 1 means that this is time, and this is a space. Okay. So we explicitly write down t and x, and then the rest of the coordinate g1, g2, g, d minus 1. Okay. So in this talk, I always pick up x as a special coordinate because I consider the entangling surface as a plane. Okay. So we split the region into left and right for simplicity. Okay. So what is the splitting? So I set the x coordinate, and then say x is less than 0 is left region, and x greater than 0 is positive region. Okay. So this is a well-defined system. And then you ask, what is the entanglement between left and right? Okay. So what do we do? Entanglement entropy is usually defined as a von Neumann entropy of the reduced density matrix associated with the region R or region L. Well-known result. Okay. So this is how you usually do it. However, this definition is completely okay for the system like spin system. But if you consider continuum field theory, we face some issues. Okay, so what is the issue? Main issue is that Hilbert space of the field theory does not generally factorize into left Hilbert space and right Hilbert space. Okay, this is a well-known issue. And this is also closely related to the fact that for field theory, in order to define entanglement entropy, we have to handle the UV divergence. Okay? Entanglement entropy in the leading order is area term, and that has manifest area divided by the UV regulator divergence. Okay, so this is well known. So anyway, what I want to say is that in order to define the entanglement entropy, we have to handle the UV issue. So natural choice is that we make the field theory on the lattice. Like putting the lattice, and then on each of the lattice, suppose we have a spin system, Hilbert space factorized, and then there is no issue to define entanglement entropy. Okay, so this is good, but for the gauge theory, we face problem. Okay, this factorization, which works for the spin system, therefore you can define completely the entanglement entropy for the lattice spin system, does not work generically in the gauge theory, which is very common theory, okay, which we use for the standard model, and also we use for the holography. So what is the problem with the gauge theory? Well, as you know, it's a Gauss law, okay? That gives a constraint on the Hilbert space decomposition. So let me go briefly over the review, which most probably everybody already familiar with, but anyhow, let's do it, okay? So for example, consider a sphere, okay? And split into left and right. So we split sphere into left region and right region. Now suppose we put the charge on the left region only. Okay, is this allowed? Obviously, no. Okay, this is not allowed because of the Gauss law. Gauss law says that in the compact space, total charge must be 0. So if we put charge only on the left side and nothing on the right side, it doesn't allow as a physical state. So it's not included in the Hilbert space, obviously. Okay. So what we need to do, we have to put the canceling charge on the right side. In this case, it's a minus sign. And this is allowed by the Gauss law. Okay. This is a state allowed in the Hilbert space. But this implies that the naive decomposition of the Hilbert space doesn't work. Okay. You split the region into left and right, and then you consider whatever left region, but that's not allowed. Always, because of the Gauss law, the excited charged state in the left region is closely tied to the right region. And due to this Gauss law, Hilbert space doesn't factorize. In other ways, we have a flux connecting left charge and right charge. Okay, and this charge, this flux, okay, or which is connection, gives additional degrees of freedom, and because of that, the Hilbert space doesn't factorize. Okay, okay, so this is well known, it's obvious, and there are several good proposals for how to handle this issue. And then one good example, which I just briefly mentioned now, is so-called the extended Hilbert space prescription. Okay, so I just follow the argument of this Ghosh, Sony, Toribedi, but there are many other good proposals before this paper by these people. Okay, so what is the problem? Okay, as you see, because of the Gauss law, left and right Hilbert space doesn't factorize. So how do you define entanglement entropy? Okay, naively in this prescription, in this extended Hilbert space prescription, as the title shows, that you extend the Hilbert space in such a way that you include a state which is not in the Hilbert space. Okay, so for example, what is a state? Like this state. Okay, you have a charge on the left side, but not on the right side. Okay, so this state is not in the Hilbert space, but because you have to consider such a state, okay, if you consider such a state, somehow generalizing your Hilbert space, then you can factorize your Hilbert space into left and right, because you can have whatever charge you want on the left freely independent on what kind of charge you have on the right side. Okay, of course, this is not physical state, but you mathematically extend your Hilbert space in such a way that it factorizes. Once it factorizes, you can calculate entanglement entropy. But obviously, because you extend your Hilbert space, you have additional junk in your entropy calculation. Okay, so you have to smartly subtract the unnecessary contribution in order to obtain the physical entanglement entropy. Okay, so this is the extended Hilbert space prescription. So I just illustrate a few examples. Okay, and then we go to the next proposal. That's our glass prescription. So I just follow the literature of this Ghosh, Sony, Toribedi. And then the final answer for the definition of the extended Hilbert space is written in this form. Okay, never mind the detail of the formula. The only thing I want to say is that there are 3 contributions if you define your entanglement entropy through the extension of the Hilbert space. One is classical Shannon contribution, and the second is a color contribution associated with a non-abelian gauge theory. And the third one is genuine entanglement entropy, which is a physical one, correspond to the number of the Bell pair through the distillation. Okay, so we are interested in only in this quantity, but if you extend your Hilbert space and then calculate the entanglement entropy in your extension, you obtain additional contribution. Okay, therefore, in order to obtain the genuine contribution of the entanglement entropy, you have to subtract this and this contribution. Okay, that's only I want to say. So let me just illustrate how this we can understand in a simple example. Okay. So just for the simple illustration, how this works, the easiest way to understand is this example. Okay. So first I explain how we understand this one. So let's consider one spatial dimension. Okay. And then gauge group is G2. Okay, plus and minus. Okay. So we have a flux in 1 + 1 dimension. Okay, in 1 dimension. Then we have a flux, which is G2 valued. So you have only plus flux or minus flux. Okay. So suppose you have 1 dimension. Say you have 1 dimension. And then you split this region into left and right. Okay. Now, because of the G2 gauge invariance, okay, we have a flux plus or minus. But because in 1 plus 1 dimension, if we consider pure gauge theory, there's no electric sources, the flux must be continuous. Okay, if this is plus, if this is plus, and if there's no electron in here, this should be plus. Okay, because of the Gauss law. But you can also consider here if the flux is minus, okay, this should be minus as well. Okay, so this is the state you are allowed. Remember that this state and this state you can superimpose into this state. Okay. Now, naively, if you consider this in the extended Hilbert space definition, this looks like total usual spin system. If you calculate the entanglement entropy, you obtain log 2. Okay. But this log 2 is not associated to the entanglement. Why is that? Because in this case, you have plus plus flux case as a Gauss law, or minus minus flux because of the Gauss law, and then you have a superposition of these two different super selection sectors. Okay, so this log 2 is associated with the super selection sector distribution in the gauge theory. Physically, once you have, say, plus flux in this left region, you have to have the plus region. Okay? So this is just simply the classical Shannon entropy associated with the distribution of the super selection sector, which is not associated with the genuine entanglement entropy. Okay, so this is a contribution which you have to generically subtract. But there's other contribution as well from the color contribution, and that is, you can understand this way. Suppose you consider one dimension as well, and then consider Noetherian gauge theory. Okay, suppose you consider one dimension, divides region into left and right, and then suppose you consider the meson. Okay, what is a meson? Meson is made by quark and anti-quark. Okay, so we have a quark and we have anti-quark, and then they are color singlet. So this A is the index for the color. Okay, in SA2 you have a plus minus. Okay, if you map plus minus for the color as a plus minus, okay, the singlet state of the SA2 is again this formula. Okay, now you may say that, well, in extended Hilbert space, this again gives a log 2. But again, this is not associated with the entanglement. It just simply means that you have a quark and anti-quark forming a meson. Okay, but the quark and anti-quark is separated by left and right. Okay, therefore, because of the color singlet constraint, you have a constraint, gauge singlet constraint. Okay, so this log 2 is associated with the color singlet constraint. Okay, but this we do not regard as an entanglement. Okay, so this also you have to subtract if you calculate the entanglement entropy in extended Hilbert space. Okay, so that's it. So I just showed how the Shannon is associated to the super selection sector distribution, and then the second term is associated to the color, okay, singlet condition, and these contributions will generically be there if you calculate the entanglement entropy in the extended Hilbert space. So you do have to subtract these two contributions in order to obtain genuine contribution of the entanglement entropy. Genuine means that the amount corresponds to the number of the Bell pair after the distillation. Okay, so that's all I have to say. So this extended Hilbert space definition is very good. Okay, it gives a good way to calculate the entanglement entropy because you by force, okay, you extend your Hilbert space in such a way that Hilbert space factorize. Okay, but as a result, if you calculate the entanglement entropy, you have additional contribution. Okay, so if you really want to understand how much genuine entanglement entropy is there in the system, okay, genuine means that the amount of the Bell pair after the distillation, you do have to do more calculation and then subtract the contribution of the Shannon and also color contribution. Okay, so that's the issue. So in this talk, instead of this extended Hilbert space, we propose another or alternative prescription, okay, which we call the Euclidean hourglass prescription. We will show later the detail, but the punchline of this prescription is that we claim this prescription is manifestly gauge invariant. Okay, we do not have the issue of the tensor factorization between left and right, as is common in the gauge theory. Even in the gauge theory, we do not have the issue of the tensor factorization issue. Okay, and this has a manifest state counting interpretation. So we do not need additional calculation as we do in the x-distributed space to subtract the unnecessary contribution. Okay, so compare with the x-distributed space, the good point of our prescription, if it works in all of the example, our method gives a direct physical entropy and then no need for the subtraction. That's a claim. And then we'll see whether this works or not. So we illustrate this in the several example, and then more complicated situation we will left as a future problem. Okay, so that's our overview. And then are there any question before we go to the prescription? Good. So let me give the prescription. So what is our prescription? So to illustrate how the prescription works, let me give the simplest example to see how this prescription came from. Okay, so this is the situation. Let's consider the field theory again in 1+1 dimension with coordinate, time, and x. Okay, again we split the region into x equals 0 into left and right. On this t equals 0 time slice, the reduced density matrix rho r is written in terms of the boost operator. Okay. So Lorentz boost is generated by this, as everybody probably know already, and this can be formally decomposed as following into the light region contribution. Okay, x is positive contribution, and x is negative contribution. Okay. So I put the minus in here so that we have minus and minus, and then cancel. Okay. So this is usual boost. Okay. How does it do in the picture? Okay. In the Lorentzian time evolution. So this is a Lorentzian time. You know, yeah, as everyone know, boost say shift the time slice into here and here and here and here. So this is t equal plus infinity. And t equal minus infinity. Okay, so boost is a generator, go upward and downward, upward in right and then down in left. Okay, so this is the usual one. And for field theory in its ground state, the modular operator is given by this boost generator. Okay, so as I said before, I split the region into right and left and then define the operator as follow. KR and KL, okay? Then K is KR minus KL. With that, we obtain the modular operator, okay? So this modular operator can formally be decomposed as a low L and low R, but low L inverse because of the additional minus sign, okay? Where low R and low L is defined in this way. So now I just for the people, I just illustrate a bit why this is a lower. Okay, so that's very easy to understand. So claim is as a boost operator, but defined only in the right region. Okay, e to the minus 2 pi of the boost operator is a reduced density matrix of the left region, and that's easy to understand. So in the Euclidean time evolution, boost operator shifts the rotation. Okay, in the Lorentzian signature, it's a boost, but in the Euclidean signature, this k is a rotation. Okay. So it changed from here to here, 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 here. And 2 pi means that this is shifted by 2 pi. So suppose you consider only on the right region, say this region, and then if you rotate it, okay, it's obvious that this is a path integration with a boundary condition fix this and this, and then you do the path integration of all over the region. But this is exactly how you obtain by the path integral method for the reduced density matrix for the light region. Okay, so it's obvious that this KR and using e to the minus 2 pi KR correspond to the reduced density matrix for the light region. Okay, good. So modular operator, which is defined in here, okay, is a good quantity, but we do not like this -1. Okay, why is that? Why is that? The quantity, the real quantity we are interested in is the entanglement entropy, okay, which is defined in the following way. Okay, now you have to be a bit careful about the normalization. So the rho r, which I defined before, okay, by e to the minus 2 pi kr, doesn't have the appropriate normalization. So you divide it by that, and then you have the appropriate normalized one for the lower hat, okay, meaning that trace with the lower hat equal 1. And this is the entanglement entropy, okay? It's the same as left and right, and you can write it down in this way. Now, this entanglement entropy doesn't have the immediate connection to the modular Hamiltonian, and that's why we are interested in the different quantity, and different quantity is a foreign. Okay. So before that, we have the modular, we have a boost generator, that's K, that's KR minus KL. Okay, that's a natural quantity. But now we define new operator called V. Okay. Note that the sign is flipped. Okay. As a result, this X becomes the absolute value of the X. So this is our definition of the V. Okay, because of V is a plus sign, okay, you have to change X into absolute value of the X. Now, I would say this V instead of K is better in the sense that to be associated with the entanglement entropy. Okay, so this is a V. Okay, now formally instead of the K, okay, modular Hamiltonian is divided by e to the minus 2 by K. Now we define the following quantity, e to the minus V instead of the e to the minus K. Okay, so the difference between V and K is just sign flip. So this gives a -1 for the K is removed, and then you obtain e to the minus 2 pi V is defined as rho L times rho R. Okay, so -1 is removed for the modular Hamiltonian. This is good in the sense that if you formally from this V define the partition function as e to the minus beta V, okay, that's defined this way. One can show that this partition functions, okay, given the partition function, and if you calculate the usual thermodynamical entropy in this system, it does match with the entanglement entropy. Okay. So in modular Hamiltonian, remember that instead of V, you have a K, and then because of that, you have additional -1. So left and right is not symmetric. But in the entanglement entropy, left and right must be symmetric. Okay. So in order to do that, instead of the K, we define V operator in our setting, and then that naturally associated with the entanglement entropy. Okay. So if you are not sure how this is related, you can check it. It's not difficult. Okay. So what is the summary so far? The summary is that instead of the K, define V formally, okay? And then V is instead of the minus, compared with the situation of the boost operator K, you have a plus, and left and right is symmetric. And then because of that, you have to handle this absolute value that is singular at X equals 0. Okay? But if you formally define in this way V, you can define the e to the minus beta V, and then from that, calculate the usual thermodynamical entropy, and that does match with the usual entanglement entropy. Okay, are there any questions so far? Good. So the goal of our purpose is that question.
Yeah, so doesn't this taking the mod of X mess with the rotation of the contour when you're going from the...
Yes, exactly. So what is happening is that, thanks to the question. So K, I write it down in the Euclidean signature. K shift this into this and this and this, right? But if you consider the V, the flip of the sign occur for the right and left region. So V is go like this. Okay, so there's a singularity in here. And that's reflected as a definition of the V. There's an absolute value. Therefore, derivative is not well defined. So this is a formula. And then later we show how you regulate this singularity, okay, in the prescription, and then ask whether this makes sense or not. That's a punchline of today's talk.
Okay.
Is it clear?
Yeah.
Good. Any other question? Okay, so the goal is that we consider this V operator. Naively, it is singular, so you have to regulate it. And then, does this make sense? And then, does it give a well-defined entanglement entropy? That is a question we want to ask in this talk. Okay, so this is the easy check how this V, this partition function, is related to the entanglement entropy. That is this one. Okay, you can check. Good. So, okay, so formally, we just shift the direction of the rotation between left and right. So pictorially, what is happening is the following. Okay, so V, okay, good. So let's focus on this quantity. This is a regulated, this is the partition function correspond to the V. Okay, what this means? Okay, before in the case of the boost, as somebody asked already, the direction of the K goes this into this way. Okay, so meaning that in the right region, suppose you go this way for the case of the K. In the left region, you go opposite way. That's for the K. Okay, but if you flip the sign, okay, into V, right region, if you go this way, left region goes the same direction. Okay, so this is a V. And as a result, you have a singularity in here. Okay, so what does it mean? Okay, so regarding this, let's see. So regarding this, okay, we can interpret this as a following way. So let's see, do I, right, good. So let me explain what do I mean by that, okay? So this is X is this direction, okay? Now we regard this square root, the absolute value of X as part of the okay. So let's focus on this quantity, okay? This is e to the minus beta B, but e to the minus beta means that you have the time circle, which is beta, but in physically, beta multiplied by absolute value of the X is the physical proper length along the time circle, okay? So instead of the beta, depend on where you are, you multiply by this weight X, okay? And then dx of the T00 is just Hamiltonian. So we regard this partition function as a Hamiltonian density, and then depend on where you are, you multiply by this weight factor, X absolute value, and then evolve the time direction, Euclidean time direction by the amount of the beta, okay? So the periodicity in the time direction is beta times absolute value of the X because of this weight. So that's what physically this quantity implies, okay? So we can regard this is as a partition function for the geometry where depend on the usual, say, cylinder, depend on where you are, the time circle is different by the warping factor X, okay? So this is a partition function on this singular geometry. That is a physical interpretation, okay? Now what we want to do is that we regulate this and then see whether this gives a reasonable partition function or not, right? All right, good. So this is a UV problem. We want to handle it. So how do you handle this UV issue? Okay, there are obviously two ways, okay? The one is very well known, that's a cone. Instead of this tip, you regulate it in this way. So you have two cones, okay? That's a standard formula. How do you handle the tip of the cone and then to obtain the entanglement entropy, okay? But this is a bit causing the issue, okay? We need, this is a bit causing the issue because if you make it as a tip, okay, obviously you are forced to tensor factor the Hilbert space between left and right because left and right is no more connected to each other, okay? So instead of that, instead of making the cone prescription, we consider another possibility, and that is instead of making it into a cone, we smoothly connect these two regions in this way to regulate the UV region, okay? So that is our proposal. And then we see whether this works or not. Okay, so again, this is all I'm saying already. We need to regulate the UV problem, somehow avoiding the factorization issue. If you make it to the cone, you have a tensor factor issue. So instead, we make it like this, okay? So the natural choice is by introducing the small parameter epsilon. Epsilon is a small parameter. We regulate the absolute value of the x, which is singular at x equals 0, into some continuum function r epsilon x in such a way that r epsilon x is x absolute value in faraway region, like here and here, should be like this. But in here, it's modified. Okay, it's modified in some smooth and non-zero value. So that's our prescription. And then we try this and then see whether it works or not. It makes sense or not. Okay, that's a goal. Okay, so we just take the simple example. Let's replace x absolute value as r of the epsilon x as this form. Okay, actually, how you regulate is ambiguity. There's ambiguity how you regulate, but you will see that such ambiguity does not influence to our conclusion so much. So in this example, we just take the simple example. Okay, this is good enough. Now this obviously behave like x absolute value at large x, and then in the small in the x around epsilon, it's modified, and then it's regulated into continuum function. So okay, so what is the situation? Now we have a regulated v, okay, by the epsilon. So before we have x absolute value. Okay, now we regulate the UV region into r of the epsilon. So instead of the x absolute value, okay, now we have the r epsilon given by this example, for example, and then t00. And then in this regulated v, we define the partition function. And then if you can calculate this partition function, it's just straightforward calculation. You obtain the thermodynamical entropy. Sorry, this is 1/2 beta d beta minus 1 of the minus log g of epsilon. Okay, that should give the entanglement entropy. Okay, so that's our proposal. The good point is that because of this, what we do is the following. Let's see. Okay, but okay, we'll explain more in detail later. But geometrically, let me see. Let's see what we did. Geometrically, the regulated partition function has an interpretation of the putting the field theory on the Euclidean spacetime with the following metric. Okay, so before we have this, but now we replace it this way. Okay, so theta is a Euclidean time circle. Okay, before we have this as a periodicity, but now x absolute value is replaced by the r of epsilon. So the periodicity is replaced by this times beta. Okay, so theta is a time circle. Now, given this metric, it's obvious that immediately you can calculate what is the square root g of the metric, determinant g and square root, and that's r epsilon. So this partition function is naturally interpreted as the periodicity in the beta direction is weighted by this square root g. Okay, that's r of the epsilon. Okay, and then you have the Hamiltonian density. Okay. So the thermal circle proper lengths depend on where you are, but we regulate it in nice way at x equals 0. Okay, so geometrically, what we are doing is the following. So before, formally, if we replace k into v, we have a singularity here because of the x absolute value. But now we regulated uv instead of the cone, we regulate it in such a way like this. Okay, so that's become like this. So remember that instead of the xe, we have r epsilon. Okay, and that's behave like square root x plus epsilon, and that's non-zero at x equals 0. And then as a result, the neck is, the waist is fatter. Okay. So it's obvious that this looks like hourglass. So that's why we say this is an hourglass prescription. So the regulator smoothes the two cones into one hourglass shape. Okay, before we have two cones, but now we regulate it in such a way it's behaved like hourglass geometry. And then the regulated partition function z as a function of epsilon is well defined and it's naturally interpreted as a partition function on this hourglass geometry. Okay, so it's a partition function on this hourglass geometry you can calculate, and then once you calculate partition function of this hourglass geometry, you can correct thermodynamical entropy, and the claim is that this is the same as entanglement entropy. Okay, so that's what we do. A few comment. Know that this prescription avoids any discussion of the tensor factorization of the Hilbert space because space is smoothly connected. Since there is no need to tensor factor the Hilbert space, the regulated entropy is manifestly gauge invariant and has a manifest state counting interpretation because this is a well-defined partition function of the theory on the hourglass geometry.
Can I ask a question?
Yes, please.
So what's the connection to normal replica method? Replica method also, we can calculate entropy using partition function.
And that's a cone, right?
Yeah,
that's multiple, singular. Right?
But is it, so if we smooth out this singularity of replica manifold, does that correspond to your calculation?
Right. So the conclusion, as we will illustrate in later, is that in some of the simple example, both hourglass prescription and then this cone replica prescription gives the same answer. But in some situation, you will see the difference. The calculation gives a different answer. The question is that which one is more intuitive, okay? And then you will see that in some of the example, more intuitive answer can be obtained in the hourglass prescription. And then cone prescription gives a not so intuitive answer. That's what you will see. So in that sense, both gives a well-defined answer. But for more intuition, hourglass works better in some situations. That's what we want to say. We will see in the example.
Probably there are several ways to regularize this.
Right, I understand.
You
right.
Have one example, is that?
Say again?
So there are probably several ways to regularize replica manifold singularity. So you give us one of.
Yeah, one way to regulate it, but this regulated is different from cone regulation because it nicely avoids the factorization issue, tensor factor issue, and also gives a direct state counting interpretation.
I see. Thank you.
Yeah. Are there any other question?
In what sense is it manifestly gauge invariant?
Okay, you see. But anyway, the point is that this G is physical partition function, right? Because this is very well-defined geometry. You can calculate what is a partition function. So you do not have to handle any of the issue of the gauge and so on. So it's just partition function on this hourglass geometry. So it's usually physical gauge invariant quantity. That's what I mean.
Okay.
Sorry. So can I ask a question?
Yes,
so when we, okay. So your idea is that connecting this left boundary and the right boundary by some, that one more type thing. So the question is that, okay, if you do that, then it will introduce the correlation between these additional correlation between these two systems. That
additional correlation is there physically because of the non-factorization of the Hilbert space, like Gauss law. That's crucial. That's crucial. But if you split it, okay, this connection by the Gauss law, say plus charge in the left and minus charge is right, and that is totally you missed it. That is a problem. But you do not want to miss that important contribution of the Gauss law constraint or connection between left and right. Therefore, instead of splitting into the two cone, we make it hourglass prescription and then see whether it works or not. That's our goal.
Yeah, but okay, okay. I'm wondering whether or not okay, if you introduce this kind of that hourglass geometry, then okay, this left boundary is okay. The entanglement entropy or density matrix is no longer invariant under this LOCC type thing operations because it will introduce this correlation.
Right, so you do not need it. You do not need it. That's a claim.
Okay.
This is our so you see that if you consider the formally V keeping this x absolute value, okay, instead of the epsilon goes to zero limit, okay, this is formally the same as entanglement entropy, right? Because V handle left and right in the equal footing. So the claim is that we regulate, okay, so the gauge invariance is maintained, state counting interpretation is possible, and then ask, does this give us an answer? That's a question. Okay, that we investigate and then see in the several examples later.
I see.
So,
okay, so can we say like this? So the bottleneck geometry you introduced is a counterpart of the the additional the lattice sites. That is introduced in the extended Hilbert space formalism?
You can interpret if you want, but that gives additional contribution and then confuse you a bit more. Because I told you in the extended Hilbert space, how to make the Hilbert space tensor factor is by introducing the additional degrees of freedom on the boundary. Right? Because of that, you can tensor factor the Hilbert space. But because of that, you also calculate additional contribution to the entanglement entropy. So in order to obtain the genuine contribution, genuine means that the number of the Bell pair after the distillation, you have to subtract additional contribution. That's you do not want to do.
Right. Then the question is, naive if epsilon goes to limit in the hourglass geometry correspond to, subtracting unnecessary, the correlation.
Automatically.
I don't think it's subtracting, right? So this prescription is doing everything gauge invariantly.
This means
so you did not.
This means hourglass.
Hourglass.
Hourglass
doing
is
everything gauge invariantly. So so you're not even extending. This is not like this place is extra degrees of freedom. You're not introducing it.
You are not introducing completely. We do not want to introduce any additional contribution, and then because of that, you have to subtract unnecessary contribution, and that is necessary for the extended Hilbert space. But we don't want to do. We want more directly straightforward calculation, which is physical, and then straightforward, and also intuitive result. That's why we try this method. Okay, so that's you are right.
More or less like a regularization of replica is a closest. Of course, difference
Another way
is
of regularization.
just difference is cutoff dependent.
Exactly. Other question?
I have a question. When you have contours where the contour folds back on itself, like you showed in some previous slide, where the right portion of the contour rotates back and goes back to itself. Comes from infinity and goes back to infinity from zero. So what happens to those sorts of scenarios?
That simply becomes a theta rotation. You see? I show you. So in K boost, it goes this, but it goes opposite, right? In V, both goes the same direction, right? Now it simply becomes regarding this as a theta direction, it's just d theta, right? So there's a warping effect depending on where you are. The length is different, but other than that, it just everything goes this way. Okay? That's the effect of the V generator. Does this answer your question? And nothing is singular.
On the left-hand side, it should go in the opposite direction, right?
No. That's K. That's K. We are now V opposite. Okay. Let me state again. Where it is. Okay. Right. So K is a rotation. Remember? But now we shift the sign into plus, so it goes this way. So it's same direction, both left and right, but there's a singularity, but we regulate the singularity by the hourglass. So it just simply becomes a theta rotation. That's V.
Yeah, my question is like when you rotate the contours, you can rotate it only by the K, not the V.
Right.
So when you,
Oh, no, I disagree. You can rotate by V. It's a theta rotation. And then we regulate. If you regulate it appropriately, theta generator is V. You can. She look at this graph. What's wrong with this? Just a moment. This generator. Do you agree this generator can exist? So this.
You had a diagram where you had this contour integral where this contour came from infinity and went back to infinity, right? Those sorts of contours you would still have in the finite temperature field theory computations when you compute, say, OTOCs or something like that, right? Those sorts of contours will still have to figure in the theory. So I'm concerned with how would you generate such contours using the KV? I mean, using the V instead of the K. So if you drop the Ks, then those sorts of contours.
No, I never say K doesn't exist. I just say consider V operator, which does exist, and that's theta direction. And then using that, we consider the regulated partition function on this, and that is useful to obtain the regulated partition function and also regulated thermodynamical entropy. And the claim is that that is the entanglement entropy. I don't say anything more. We just need V to calculate the entanglement entropy. That's all I want to say.
Okay.
We can also consider other K and as well, but that's not my focus. Is it okay?
Yeah.
Okay, good. So we just focus on V, and that is this theta direction. All right. And the good point is that as Tomonori say, we do not need any additional degrees of freedom. That makes that calculation simple. Okay. Good. So that's we want to calculate, and then we want to calculate the regularized partition function. Okay. So that's all I say. Okay. So I just skip this slide. And I also skip this one. Okay, so I just comment with some question regarding some question. So let's compare this with a comp prescription. Okay, notice my time is now limited, but let them continue. Compare with a comp prescription. What do you do in the comp prescription? Okay, so comp prescription, instead of this, you make it to the two smooth cone. Okay, that's what you do. You can regulate appropriately, and so this is a comp partition function, and then you just consider only this part. You don't need to divide by half, and this is a entanglement, and usually you define. Okay, as I say, that this has an issue of the factorization because you you disconnect the left and right region manifestly. So you need to tensor factor unless you put the additional degrees of freedom on top of the tip. Okay, but this is how usually you do. Okay, and because of that, it doesn't necessarily give the state counting interpretation because of the issue of the additional degrees of freedom. Okay, now how do you see the example? Okay, I show later. Okay, my later, I don't have so much time, but this can be shown in the, say, scalar fields with non-minimum coupling to the curvature. Okay, so suppose I consider the scalar field theory, okay, phi, but it coupled to the curvature, say, G phi curvature. You can consider such a theory. Okay, what does it mean? Okay, because of this additional curvature coupling, even if you consider the entanglement entropy for this scalar field, which has a non-minimum coupling to the curvature, if you use a cons prescription where you regulated this region into this, you pick up some high curvature contribution. Okay, even if you consider the entanglement entropy on the flat space, in cons prescription, you consider that you pick up the contribution of the high curvature into your game. Okay, as a result, if you use a comp prescription, your final answer for the entanglement entropy does manifest dependence on the GUG. Okay, because even if you consider the flat space entanglement entropy, because at the chip you have a curvature, and then if you consider the scalar field coupling non-trivially to the curvature, the result of the entanglement entropy has manifest GUG dependence. Okay, but that is very counterintuitive. Counterintuitive, why? Because we are considering the entanglement entropy on the flat space. Okay, flat space entanglement entropy has a curvature equals background. Therefore, its entanglement entropy, or more or less its wave function, should not be influenced by this GUG. Okay, so intuitively, it is more natural to obtain the result of the entanglement entropy for a scalar field theory, which has non-trivial coupling to the curvature. But as you consider the entanglement entropy in flat space, the result of the entanglement entropy should not depend on the GUG. But if you do the comp prescription, because of the tip which pick up the curvature contribution, the result of the entanglement entropy pick up the GUG dependence. So what I want to say is that the result using the hourglass prescription gives a more intuitive answer compared with the comp prescription. Okay, that's what we will see in the later example. And this is related to the Maxwell field theory, which also lead to the negative entropy. That's very counterintuitive. And when you put on the comp, that's so-called the Kabata. Okay, that's a long paper. Okay, so we consider the scalar field in 2-dimensional later with non-minimum coupling to the curvature. I already mentioned. Hourglass and the complexion gives a different answer. Cone gives a coupling constant dependence, even though you consider the entanglement entropy on the flat space. But hourglass prescription gives a no dependence on the coupling, and that is intuitive result. Okay, so that's what I want to say. Okay, so that's all I want to say for the prescription. And now, okay, in the rest of the 10-15 minutes,
but those are cutoff, right? Those are cutoff physics. So depending on how cutoff works, it might depends on the. So I mean, it's just a different prescription. It's everything is
right. So we want to see the cutoff insensitive part as much as we want. Say, for example, in many of the example, you are right. You are completely right. We consider the 2D example. Then we have the epsilon dependence, but this coefficient we expect to be independent of the cutoff, and that's what we are interested in. You are right.
Yeah, but I cannot answer from low energy point of view anyway, because it depends on how UV is really cut off. If the cutoff of UV depends on curvature and so on, depends on Z, correlated with Z, then after cutoff you will. So all these are cutoff physics.
No. Okay, so let me go to quickly the example. Okay, to convince you, just bear with me. So where it is. Okay, so we consider this example. Okay, so this is a 2D theory, 1 + 1D.
Yep.
We have a non-trivial coupling to the curvature. Okay, now we ask what is the entanglement entropy in this system. Okay, so here's the result. Okay, good. So hourglass gives us this result, and cone gives this result. See, we are looking at this contribution. So cone gives this Guji dependence, but you are worrying about the cutoff dependence. Cutoff dependence is here, but it doesn't affect here. Right. This coefficient is cutoff independent part. If you do the cone prescription, it does depend on the Guji, even though you consider the entanglement entropy on the flat space. But if you do the hourglass, instead of the 1/6 minus Guji, you obtain simply 1/6.
Well, you're saying log 1/m infrared. Yeah.
I mean, this one. This is cutoff independent part.
Yeah, it's infrared.
Right. So the claim
it's
is
not part of physics. Okay. Yeah.
It's not part of physics, exactly. So what I want to say is that we are looking at the cutoff independent contribution, because obviously it depends on how you regulate it. So as you look at the cutoff independent part, then you see the difference between cone prescription and hourglass prescription. And then there's a difference, but the hourglass gives a more intuitive answer. That's what I want to say.
Not just more intuitive. Are you saying that cone prescription is wrong?
I hesitate to claim that.
But it's a different answer.
It's a different answer,
and it's not the cutoff physics.
Counterintuitive. It's counterintuitive. That's what I would say. I will not brave to say it's wrong, but it's a counterintuitive. The reason I want to understand this issue is that because we always have to handle with I tell you the simple motivation. In the extended Hilbert space, you have to subtract, okay, because of the additional junk with that. My guess is that even in the cone prescription, you have the additional contribution coming from the curvature contribution at the tip. You probably have to subtract something in order to obtain intuitive answer. So that prescription might be needed for the cone prescription, but in hourglass, everything is automatic. That's what I want to say. If it works in all of the example. We just study a simple example, but so far it works. That's our claim.
I think about your question.
Okay. Any other?
I will think about.
Yeah. Okay. So I already mentioned some example, but let me go to several example. So Sekino-san, how much time do I have?
So maybe 10 minutes.
Okay, sounds good. So let me go back. So I already mentioned the prescription. Hourglass is better in the sense that it's natural, state counting, gauge invariant, no issue of the factorization. We study in simple planar entanglement plane in many of the examples, and so far it works. Okay, more complicated entanglement surface or many multi-boundary issue is work in progress. Okay, so I show the several simple example, then try to convince you. So far it works. Okay, so first one is extremely simple one, is a 2D CFT, okay, on the compact region, and this is like open string. Okay, you have open string. Then we split into pi over 2, pi, right and left. Okay, that's simple example. Yeah, it's always better to start with a simple example. We know the Virasoro, because the textbook of the Greenshot was written, left and right. Okay, K is this, very natural quantity. Everything is regular, you don't need the regular, but we want to V. Okay, so what do? Absolute value. Okay, that's called the singularity. So you introduce epsilon and then you regulate. Okay, it's automatic. So this, and then regulated. Okay, then what is the structure? Okay, you regard this. So in the end, you want to consider e to the minus beta V. So we just multiply beta, and that's the argument. Okay, so that's you regard as a beta, as a theta direction integration, but you weighted by this factor. Okay, now this you regard as a square root of g of the geometry. What is the geometry? And that's the geometry. Okay, so that's like our glass as a neck. See, this example around the sigma near pi over 2, it's like sine. You see what I mean? Cosine is like this, from 0 to pi, and near here, half pi, it's like sine. So it's like sigma minus pi over 2, and that's exactly like the previous example. Okay, so that's exactly the same. Okay, so we have V. Okay, we calculate what is a regulated partition function, and then we evaluate the thermodynamical entropy of this regulated partition function. It's straightforward. I will not, okay, I can show you the result. Okay, so we have this geometry. Okay, sigma is 0 to pi and theta is 0 to beta, but we do the coordinate transformation. Okay, we do the coordinate transformation here in such a way that it's mapped to here. It's easy. Now, in doing this change of the sigma to y, sigma is 0 to pi, but y becomes 0 to L, but L is this quantity, and that goes to infinity, in the epsilon goes to 0. Okay. So after the change of the coordinate, we have the situation like this. So originally we have this, our glass, and this is beta, and this is pi. And you split left and right. But after the map, you have overall factor, and that's this one. And then it's become simply cylinder. Okay, but cylinder here theta is beta, but this direction become L, and that goes to infinity by the logarithm. Now we want to consider the limit where epsilon goes to the limit. But that's the same as you consider the long string limit, long cylinder limit. Okay, in the long cylinder limit, you can use the Cardi formula. So the partition function of this long cylinder limit is easy to calculate. We neglect the conformal factor because we are considering the conformal field theory. The factor doesn't matter. Okay, so you obtain the partition function. Easy. Then plug in the relation between LE and epsilon, and then evaluate the thermodynamical entropy as 1/2 beta d beta minus 1 minus log of g. Okay, you obtain this. And that does match with the intuitive answer of the entanglement entropy. Okay, so that's example 1. Now let's go to the next example. So this is a previous one is a conformal field theory. We consider the massive scalar in 2D. It's not conformal field theory. Okay, so we consider the regulated partition function, the same as before. Now, instead of the compact space, we consider the infinite distance, x negative and x positive, and the infinite distance. Okay, so the geometry is here. But you can do again the coordinate transformation, x into y. Okay, then again we have this factor and then this. But now, because it's not conformal invariant, this factor is not negligible. So suppose we consider the massive scalar field in 2 dimensions with this metric. Okay, this and this is just change of the coordinate. It doesn't do anything. In this coordinate, the partition, the action is this. Okay, we are looking at the regulated partition function on this geometry. So you can do it by path integral, and you just you need to evaluate the determinant. Okay, we consider the free theory. And this the determinant you can obtain. Okay, it's simple exercise. Okay, we go to the theta direction as a thermal circle, and then go to the Euclidean Hamiltonian description. Okay, and since we are handling the boson, it goes to the Bose Einstein statistics, and then partition function can be evaluated given the eigenvalue. Eigenvalue is determined by the Schrödinger equation, whose potential is determined by this. Okay, so the question is that let's see how this goes. The potential is okay. This is standard technique. Given the regulated partition function, you can do in terms of the density of the state, and that's not typically just usual quantum mechanics exercise. So the potential behave like this, and then in the limit, we consider the fixed omega. That's omega square, because omega square with this potential. Okay, it's approximated by the size L of the wave potential, and the size is determined, and then you obtain what is the density of the state. Usual story, nothing fancy. And then you obtain the density of the story, you evaluate the partition function, the result is following. Okay, so the result is the same as consistent. So that's example 2. It works not only in the common field theory, even if you have a mass, it works. Okay? We don't consider the interaction because it makes the path integration complicated, but you can do part of it. And now third example is the one which I already mentioned. It is the two-dimensional scalar field theory, but you have a non-trivial curvature coupling. So the question is whether this G, the curvature coupling, plays a node or not. Okay. If you consider the entanglement entropy on the flat space, okay, then R equals 0. So it should be no effect to the wave function by the G, because we are considering the wave function of the flat space. Okay. Then it's obvious that entanglement entropy should be independent of the G, as you consider the field theory on flat space. Do the straightforward calculation, very similar to before. Only effect of the G is that in the previous example of the Schrödinger equation, potential is slightly shifted. Okay, that's exactly the same, and it gives some bump, but you can show that in the epsilon goes to 0 limit, the size become very, very large, and compare with the size very, very large, this small bump is always negligible, that you can show in many ways. Okay, so at least in the epsilon goes to 0 limit, the size, compare with the size, this bump is negligible. That is equivalent to saying that G, the curvature coupling effect is negligible in the leading order in the large epsilon, and then the result is insensitive to the G, and that's what we obtain. Okay, so this I already mentioned. The coefficient, which is UV regulator independent contribution, is 1/6, and no dependence on the cutoff, and no dependence on the G, that's a curvature coupling. Okay, but compare with the Cohen prescription, that gives the additional one. So we see there's a discrepancy. Okay, I will not say which one is physical or not, but just gives a different answer. So in order to interpret what is a genuine entanglement through the distillation, you have to be careful. Okay, but our graph gives a more intuitive and direct answer. Okay, we continue to the Maxwell field in 2D. Okay, physically, Maxwell field in 2D, just pure Maxwell field. Intuitively, there is no local degrees of freedom. So whatever you do, you expect the answer should be, instead of the minus negative quantity, entanglement entropy should be 0. Okay, and in fact, our graph prescription manifestly gives this is 0. Okay, and that's obvious. But in order to understand the effect of the flux, okay, we consider the effect as well as the flux is there. So the situation we're considering is that we have a 1D, we split region into left and right, and then we put the charge. Okay, there's a non-trivial flux is there penetrating left and right region. Okay, so this is a region where this is a situation where the difference manifestly enters the story. Okay, in the Cohen prescription, okay, suppose we have a 1D, we have left and right, and then if you have the flux charge source, I say this is minus, I say this is plus Q according to this formula. Okay, there is a flux penetrating. In order to do the Coulomb prescription, you need additional local degrees of freedom to put at the tip. Okay, because of the Gaussian constraint. But in hourglass prescription, you do not need to do such a thing at all. Everything is automatic. As in this setting, you calculate the physical partition function, but intuitively, physical partition function on this hourglass should be 0 because there is no local degrees of freedom, even though there is a background flux. That's intuitive. Okay. And then you calculate the partition function, stress tensor is there because of the flux, non-zero stress tensor is there, but V is just some constant associated to the flux. Okay, and then partition function is simply beta times V, that is some quantity proportional to the beta. Okay, that's a regulated partition function. Because V is just constant, which is non-zero. Okay, and because the V is constant, you obtain exponential minus beta times some constant. Okay, now it's intuitive that this simply shifts the ground state energy, okay, but doesn't do anything for the entropy. Okay, or mathematically divided by beta derivative and times beta, and then subtract -1. Obviously, you get 0. Okay. So this simply gives the energy contribution, vacuum energy contribution, but it does not give the entropy, and that is intuitive result. Okay. So hourglass prescription automatically gives a state counting and also gauge invariant result. Even there is a situation, even in the situation where there is a flux penetrating right and left. Okay, so that's good.
I have a question.
Please.
Why are you integrating from minus L to L? You shouldn't you integrate from minus infinity to infinity?
Yeah,
Because electric field.
Right. You are right. You are right. We just introduced IR regulator. That's the only reason. You are right. You are right. We send L to be big in the end. But for this calculation, we just introduce the IR regulator. That's the reason. That's only because otherwise it's become infinity. We just need a regulator. That's it. That's the only reason for minus L to L. Okay. All right, we can do higher dimension as well, but I just skip. Or I just mentioned the result. Okay. Higher dimension scalar field, but assuming that the entangling surface is a planar. Okay. We split the region into left and right in x coordinate. Okay. In higher dimension, you obtain some result of the entanglement entropy. Okay, that's consistent with the universal area law. Okay, of the entanglement entropy. But if you consider the Maxwell theory in higher dimension, okay, what you obtain? Okay, intuitively you have the Maxwell theory. Okay, we split into the two-dimensional contribution, and then D minus two-dimensional contribution. You may say that there's a D minus two-dimensional contribution associated to the scalar, and then the result of the hourglass prescription gives exactly that result, meaning that the Maxwell theory is entanglement entropy calculated by the regulated partition function on the hourglass geometry, then evaluates the thermodynamic entropy, and that is D minus 2 times simple scalar theories entanglement entropy. So that is also intuitive result. Okay, so that's the result of the Maxwell field theory in higher dimension. So let me conclude and summary. So hourglass prescription avoids any factoring of the Hilbert space issues. Okay, instead entropy is defined in terms of the full Hilbert space. You do not need to split the Hilbert space into left and right. Therefore, if you regulate appropriately, okay, you do not need to introduce additional degrees of freedom. You do not need to subtract unnecessary contribution. It's just straightforward, straight counting interpretation as a partition function of the regulated geometry. And then given that you consider half of the von Neumann entropy of the density state. Why half? Because we have full contribution of the both left and right. So to obtain the entanglement entropy, you divide it by half. You divide it by 2. Okay, that's a physical integration. Okay, so everything is regulated quantity, regulated partition function, no issue. So density matrix has a thermal interpretation correspond to the position dependent proper temperature. Because of this, I already mentioned. That's exactly this picture. So this is hourglass. That's why we call it hourglass prescription. Okay. And I think I already mentioned all of these. Good. So this is more or less my last slide. So hourglass has a freely reacting killing vector d theta. And this means that local geometric quantity like curvature will be independent of the theta. Okay, there's an isometry of the hourglass. That's theta direction. Okay. Then if you add any local term in the effective theory, okay, because we have the isometry along the theta direction, the effect of the local term contribution to the effective action always ended up to the proportional to the beta because of the theta integration. Okay, but this something, some constant contribution from the local term times beta only contribute to the energy, but not to the entanglement entropy. Okay, so that's also intuitive. On the other hand, putting the field theory on a cone and varying with respect to the deficit angle, okay, the killing vector on a cone has a fixed point, okay, at the tip. This means a local term in the effective action can, okay, contribute to the entropy, and that is a bit counterintuitive. So that gives a manifest difference. So, okay, I'm sorry for giving a bit more going beyond the time, but just future work, which we are doing, I just announced it. So we obtain the area law result in higher dimension, and then looks like that this coefficient has an interpretation of the area and then connecting the entanglement entropy, the number of the degrees of freedom. So the question which we are wondering is, are there any connection to the C theorem? Okay, or we consider only the planar entangling surface, but you can also consider the spherical entangling surface. And does this has a nice holographic interpretation as Lukowitz, Marlasen, and so on. And these are the work in progress. And that's it. Thank you very much.
Thank you for a very nice talk. So if there are quick, urgent questions, you could ask here. But if not, maybe we can close the session here. And yeah, if you have time, you can go to the spatial chat that Tadashi just send the link on the chat. So you could
ask one question, because I think it's related with what I asked.
I can stay here for a while. So if you have a question after closing, I'll be here and then I can talk. That's also we can.
Yeah, that's good.
So you close and then I'll be here for a while, so we can still keep talking. That's okay.
Yeah. Anyway, so yeah, if people want to leave, you can leave. So, thank you. Yeah, so please, Nomura-san.
Oh, hey, yeah, because I'm just a bit confused, and then saying that usually I agree that the coefficient of log m term is usually said to be cutoff independent. That's true, correct? Okay. But the answer you get was depending on cutoff, right? I mean, our grass gives 1/6. And the other one gives 1/6.
Let me clarify. So Guji is not cutoff quantity. Guji is just coupling in the effective action.
Yeah, I agree. So that's why it seems like coefficient of log m is not cutoff independent, because if you change the cutoff, it depends on infrared coefficients. So
let me add a bit more words. So when we say cutoff dependence, but if you do the cutoff, okay, so here what I mean. So suppose you have the tip behavior, and then if you regulate it this way or regulate it this way or whatever, these are the detail. How you, once you split into the left and right by the cone, how you regulate the cone, that does not affect the log coefficient. That's true. But regulating this into this or this is totally different.
Yeah, so but that means that usually cutoff independence means that if you keep all the same low energy symmetry or something, right? Otherwise, this anomalous
symmetry is different. Symmetry is different.
It's different,
right? Because this is Hilbert space is extended into whole space, but here it's not. It's manifestly splitted because left and right is disjoint universe. So symmetry is totally different in
At the raw energy, is it?
in the inner, right? Because see, this is a point. Yes, let me explain. So suppose we have this.
Then it's a different theory, yes.
Yeah, suppose we have this. So in some sense, cone gives a different theory. Because of that, you have to subtract additional contribution. So let me repeat what I want to say. So in this theory, suppose you consider the, say, Hilbert space. You agree that we have not only vacuum, but also we have plus and minus state as well, right? But now if you do the splitting regulated by the cone, what do you obtain? You obtain this and this, but you have plus and minus. Is it allowed? No, because in this space, you have only plus charge and you have only minus charge, but that's not allowed by the Gauss law constraint, right? So what do you need? In this case, cone, you do need additional minus locally here, additional plus.
Yeah.
So manifestly, Hilbert space is different. But on the other hand, if you do regulate in this way, you do not need to do anything, plus and minus. So it's an issue of the UV, but it's significantly influenced to the IR because of the Gauss law constraint.
What's the Gauss law constraint in this example?
Say again?
What's the Gauss law constraint in this example? This is a scalar field on the just background.
Oh no, this is gauge theory. This is gauge.
Yeah,
theory.
of course I understand, but I'm saying this specific example.
Right. So in this
you get the
gauge
1/6 and 1/6.
So I want to say that in this gauge theory, if you split this into this, and then you keep plus and minus, that's not allowed. That's not allowed manifest.
Yeah, that's why you have to subtract the Shannon term and so on.
But you have to add that you have to add the local degrees of freedom. That is not there in the original theory.
Yeah.
So in that sense, the IR theory is totally different.
No, yeah, of course. So, but what I didn't understand was this example of Z and non-minimally coupled scalar. And if you just change the regularization and no Gauss law constraint,
because it's a scalar
field,
yes.
and still you get a different answer in what we usually think cutoff independent term.
Okay, good.
That's the question. Yeah, that's what I don't.
That's a very good question. I do not have so intuitive answer. Only I can answer is mathematically. Mathematically, I can give the sharp difference. In the cone prescription, you regulate the tip of the cone, but you have to pick up the contribution is curvature singularity, deficit angle contribution. That manifestly does contribute to the curvature coupling. As a result, entanglement entropy does depend on the curvature coupling. Okay, mathematically, there's no doubt for this calculation because you have a curvature singularity because of the deficit, and that does contribute to the entanglement entropy.
Is it true? Because if the low energy, everything looks same, and then I kind of felt that cutoff independent piece must be the same. So for example,
it's a change of topology. You are right. It's a change of the topology.
No, topology at the UV. So from low energy point of view,
topology is IR quantity. You do care whether this or this. There's a topological contribution. That gives the difference.
Yeah, you change the topological index. That's what this Xi R does.
Right.
Is that so? It's not. So it's actually you guys are claiming that infrared is a different kind of.
Well, obviously,
different background.
That is different. Yeah.
But
Topology is different means that the theory is different, right? Generically. Topology on the field theory labels is different, means that it's a different theory. That's a significant point.
So entropy is not observable quantity. Because if it's observable, you can see the topology at short distance just by measuring something at infrared.
Let's see.
If we quantize this, scalar field with curvature correction, like R phi square, on flat space, there are no contribution from R phi square.
Right.
And we can just calculate the entanglement entropy, just real time formalism. Then we don't see any extra contribution.
Oh, you say in the real time
Yeah.
There's a contribution.
I thought so. That's why I wanted to know your calculation. Suppose you get the R, you put the singular R, the non-zero bev, and then it will shift phi, right? Shift phi position dependently. So you really have to do everything carefully. And then my question is, my sense was that you get the same answer. But if you do it just to put in background without shifting anything, then of course. But if you have a tadpole and just the position dependent, I just really wanted to make sure that your claim is right. So that's why I'm asking, because it's counterintuitive. Like
I agree, it's counterintuitive, but I think this is true. You have a curvature coupling, you regulate the tip into the cone, smooth cone, and then but still there's a curvature contribution, and that does contribute to the entanglement entropy calculation, at least for the static case. And then you can do not only for the curvature coupling, but also as a Maxwell's case, and you obtain strange negative term. That's a covered term case. But I think this calculation is, as I see, it sounds reasonable or correct.
But you understand this negative term as a Gauss constraint, but we don't understand here. So that's the difference.
Right. So if you do the cone prescription in Maxwell's theory, you obtain the negative one. But if you use the hourglass one, you obtain 0.
But we understand that why that's the difference. But here I didn't understand. So
but hourglass it gives 0. So that's you understand, right? It's intuitive.
Yeah, probably hourglass is right, but I just want to understand if it's really yeah.
And also I would mention that our prescription is only for the planar. It makes sense to consider more generic entangling surface as a sphere and see whether it works or not. So far we are checking on some of the works. It looks promising, but we'll see.
Okay, thanks.
Matt, do you want to say something? I saw a chat.
I don't have much to add. I just wanted to say that I don't think it's a question of having two different theories. I think this just notion of entanglement entropy is not a uniquely well-defined thing. And so I think you're just calculating two different quantities.
I agree. But if you ask how much genuine entanglement, like after the distillation, how much you have the corresponding, that is physical quantity. And I think that has a unique answer. That's what I feel.
Okay. Yeah, that's what I meant by entanglement entropy you calculate is not observable.
Right. Depending on the geometry, topology, maybe you obtain different answer. But the curious answer to me is that the genuine quantity. And so far, hourglass one looks like this genuine quantity. That's all.
Okay.
For gauge theory,
I have a more basic question.
So in the initial part of your presentation, you have 3 terms, right?
For the extended one, yes.
Yeah. And then you only pick up final one in your calculation?
Good. So okay. So in some of the simplest example we see so far, looks so, but in more complicated example, we need to check because I tell you the reason. So let's see where's the slide. Sorry, just a moment. Right. So in extended one, you have a 3 contribution, but we are interested only in this quantity. Now, this you can do in the mainly by doing the entangling surface on the sphere case. You can evaluate this in more precisely in many of the higher dimensional gauge theory. But so far we do only the plane. So in order to check with this comparison, you have to do the calculation on the entanglement surface as a sphere.
I see.
And because of that, we are working on the entanglement
the
sphere case and then want to compare.
If we choose subsystem to be spherical, then you get the logarithmic.
Exactly. And that's we are interested in. Right. That's we are interested. That's why we want to do the spherical entanglement situation. That's why we say as a future prediction.
I have a more basic question.